Hello, guys, girls, everything in between. Welcome to the 3CL4 final review. Before I begin this, a massive apology from my side for the extreme delay that this went through and the kind of half-baked problem-solving session. I had a lot of technical difficulties during the problem-solving session, and my device just kept screwing me over. And that meant that I spent way more time than I'd like to admit trying to fare up the questions that I'd done, only to get angry and give up at it. So I only got it like finishing up this presentation at about 9 p.m. or thereabouts. But rest assured, I will try and post those final solutions as soon as I can. So let's get started. This is what I'll be covering in this. I'll be covering some basic theory. This is enough to just get your feet off the ground, and you can start hard solving as many problems as you can. I also did the solved problems, and I'll be firing them up later, and I'll be giving a few tips on how to do well in the exam. I want to re-emphasize that this is a very, very technical presentation, and I will not be going into any sort of detail. There's like less than 30 slides on here, so please don't rely on this as your only resource. I hope that you look at it as more of a springboard. With that said, this is how you get good at 3CL. If you are in the mood of wallahi I'm finished, I understand, because the main reason is there's too many things to look at. I would say prioritize, start with the study notes. I think Eamon has posted them. I think Arthur has also posted something similar. That'll give you a quick checklist of what to do. Then go into tutorials, go into the past papers and the recordings that Arthur has already recorded. Do the recommended problems that you have done already. If you have done them, good. If you haven't, go and do them. Check on your labs and try to do labs 4 and 5 with frequency domain if you can. That was also recommended. And then you can touch on everything else if you have time. So let's get started. Course content. Let's begin with the introduction. What is 3CL? Basically anything that can be modeled using a process and can be controlled using a controller. This course is control systems. The actual output of the system is never equal to the output that you want it to be, because life isn't fair and everyone sucks. There's always noise, there's always disturbances, and even then our goal is not to get perfection, it's to get close enough, and we define that using performance parameters. Everything over here on the right is what you're expected to know before coming into this course. If you're weak on any of these, I would say it's kind of late now, so might as well realize that you're not going to be getting so good in those questions when they come in the exam, and try and focus your attention on the other ones. So let's get started. Modeling. We always need a differential equation. We need some way to relate a change in a variable and a change in time. The two big ones that we have are springs and dampers. There's always a billion others, but this is something that you want to remember. In this case, LR refers to the rest length, X2 refers to the second position that we're measuring, the final position, X1 refers to the initial, or the first position that we're measuring, and the theta applies to the rotational effect of a spring. Springs also apply a counter torque when they're rotated. Theta and phi here refer to angles. In a damper, X2 prime and X1 prime refer to velocities. And of course, there's the Newton's law of motion, which ties everything together. That is to say that the net force is equal to mass times the sum of all accelerations on the body. This is very rarely used because time domain is clunky and bad. We usually just shift everything to the S domain. This is not to be confused with Fourier's S domain, though we do touch frequency response, but that's still not the same thing. The reason we use Laplace transforms is instead of using differential equations, we now use transfer functions, and instead of using evaluating y of t by hand, we get step responses or ramp responses in terms of S. In this case, model accuracy does play a big factor. If you've done the labs, you know that sometimes we approximate things to second order models and so on and so forth. So similar to how in differential equations we sometimes have to make approximations, we sometimes have to make approximations in transfer functions as well to simplify our analysis. I didn't have anywhere else to put the slide, so I'll just put it here. If you see a block diagram, you guys are familiar with what a block diagram is. It's this guy over here. This is a block diagram. You can simplify it using these rules. I doubt they'll ask a question on this, but because I'm saying I doubt it, it'll probably come. So a quick way to just look at the slide. So transfer functions are a way to express how outputs are related to inputs in the S domain, similar to how differential equations work. The golden rule for a transfer function looks something like this. A transfer function is written in terms of a gain term, k, and a multitude of products of zeros and poles. Poles in the denominator, zeros in the numerator, the factors of the numerator and denominator functions respectively. These are complex numbers. They can be real, they can be imaginary, and their values are what dictates this big chart on the right. This big chart on the right is what we spend the entire course studying. So if you have a pole right here at the dead center, I'm looking at just one singular pole for this entire analysis, but this does apply to a majority of others because of the dominant poles and stuff like that. So if you just have one pole, you'll have a flat line if you have a pole at the origin. If you have a pole at the left of the origin but still on the real axis, you're going to get a descending curve. The more further you go, the faster this curve descends. Similar on the right, you get an ascending curve. The more further on the right you go, the faster the curve ascends. If you have any complex terms, the complex terms will always appear as complex conjugates. There's going to be one here and there's going to be one below it. For these, if you have just a complex conjugate, you're going to get a sine wave. If you have more of a complex conjugate but still no real term, you're going to get a higher frequency sine wave, because j omega, where omega refers to the frequency, you're obviously climbing in omega, so you're going to get a higher frequency. As we go to the left, you encounter this decaying behavior. You'll notice that this curve and this curve's dotted line match exactly the same. This is because you can think of this as one step along here and one step along here. So you have a sine term plus you have the decaying term, so you get a decaying sinusoid. This is a quick way to plot responses. Another thing you want to remember is the final value theorem. That is to say that the value of a function in time domain at t equals infinity is the value of a function in the S domain as s equals s goes to 0, sf times s. Only works if the system is stable. More on that later. So we work with a lot of second order transfer functions because they're easy and they're a good approximation between first order uselessness and third order insanity. A few things you want to know. This is how a second order transfer function usually looks. You have an omega n squared term, you have s terms in the denominator. Obviously, the second order means s squared. There's no numerator 0 here. The standard form of the roots of the denominator is this. This is a quick way you can derive, put this in a formula sheet. This is the different ways we describe a system. So we have underdamped, overdamped, and critically damped. These are used in many other places like 2EI. We've used this in 3G and so on. So you should be familiar with this. Another thing we use this is, I mentioned performance parameters earlier. We use performance parameters over here. You can find the peak rise time for a function. So we can find the time that it takes for a function, for a response to peak. So this time, we can find its value, and we can also find the settling time, and we can also find the damping ratio using the and the angle using theta equals cos inverse of the damping ratio, which is, so this is the damping ratio, this is the natural frequency. You are familiar with these terms already. A couple of things that I mentioned about approximations. If you have a pole, if you add a pole to an existing second order system and the pole is much greater than zeta omega n, then the complex poles will dominate. If the pole is much less than zeta omega n, the pole starts to dominate and you can ignore the zeta omega n as a system. And if they're close, then you can't really make an approximation. You will have to consider everything, and then it becomes a bit more complicated to model. Of course, the closer you get to zeta omega n, the worse this approximation of turning the third order system to a second order system gets, because when you add a pole, you make it a third order system. Moving on, a quick addendum. I mentioned about every performance parameter, but I didn't mention about steady state error. Steady state error is this guy over here. This is the steady state settling time, but the final delta value is steady state error. Steady state error of a system depends on the type number of the system. So if you have a G of S, and if it has any terms inside of it that are just an S, or an s squared or an s cubed, that is the type number. N is the number of origin poles. Depending on the type number, you get a different steady state error. The best system is obviously one that has the most number of integrations, so this, but obviously this is harder to achieve in practice because you'll have to have your controller add those poles into the system, because systems don't just give you poles for free. And you might want to keep an eye on Kp, Kv, and Ka. You will be using these across the course. So let's talk about stability. A system is stable if and only if all bounded inputs give bounded outputs. A bounded input is an input that has a defined range. So if I put an input of, let's say, x squared, that's not a bounded input because it can go to infinity. But if I put an input, let's say 1 or 2, it's just a step input, right? That's completely fine. If I put an input of sine x, that's a bounded input because it'll only go from -1 to 1. If every single bounded input you can put into a system gives you a bounded output, the system is stable. Bounded outputs are the same condition. So that means that if I put in a straight line and the system outputs something like this, then it's not stable. This is really bad. The condition for stability is that all poles must be in the left half plane. So as I mentioned over here, this is the LHP, this is the left half plane, and if all your poles are in the left half plane, that's what you want. You want your poles, the poles are usually marked as X's, you want them to be in the left half plane. If you have poles on the j omega axis, it turns into marginal stability, and we don't count that as stable in this course. So if you have it on the axis, it doesn't count. A quick way to evaluate stability if you can't derive all the poles is to use the Routh-Hurwitz condition. A system is stable if its RH table has no sign changes in the first column. What the fuck? Simple. You want to get the system transfer function and only look at the denominator. We call this Q of S. You can consider this the characteristic equation. A characteristic equation is an equation that's used to work on a certain theorem. So in this case, Routh-Hurwitz theorem uses Q of S as a denominator. Make a table with n plus 1 rows. N is the degree of the denominator, and rows are labeled from n to 0. So you have row n, row n minus 1. So if you have a fifth order system, it's going to be 5, 4, 3, 2, and then 0, 1, 0. Fill the first row with the coefficients of s of n, fill this, and then s of n minus 2. So skip one power. The second row is s of n minus 1, s of n minus 3, and so on. The third row is the determinants of the above rows. So for example, in the third row, this first element is going to be this element, this element, this element, this element. So if this is A, B, C, D, minus 1 by element above, so minus 1 by C, sorry, A, B, C, D. You guys know how to evaluate a determinant, just evaluate this determinant and you can get this answer over here. Similarly, the fourth row, the fifth row, and the sixth row, whatever you have, are going to be evaluated the exact same way. If you find a zero element, this poses a problem because the next element below it is going to be infinity because it is 1 over 0. You can solve this by taking the element as a very small number, e approaching 0, and write every term in terms of that. If you have a row that is fully 0 though, this is a result that you can use, so you can't use the element result of the entire row as 0. If you see an entire 0 row, you can say that the roots are radially symmetric. That means that there's a 180-degree angle between them, something like this, or like this, or like this, or they could also be on the axis. Usually these are either this way or this way. They're either on the j omega axis, making the system marginally stable, or they're a pair on the real axis, which means they are unstable since one of them always has to be greater than or equal to 0. To deal with this, we take the non-zero row above it as an auxiliary polynomial, and the highest power of s becomes the row number. So if let's say if row, if I have going back to that previous example we have, if I have the 5, 4, 3, 2, 1, 0 rows, and I know the third row turns out to be a 0 row, I take the fourth row, which means it is s to the power 4 plus s squared plus something and so on. I'm going to put in the coefficients like 3, 69, whatever, and I will take its derivative. This is going to become 12s cubed, and then 69 times 2 evaluates to, well, something like 138, I'm not sure. And this will become your new row. This auxiliary polynomial a of s is actually a factor of q of s, the original denominator, and its zeros are actually going to be poles of the original transfer function. So if you divide q of s by a of s, you get a new polynomial that gives you more a simplified way to find roots of the original transfer function and to find poles of that transfer function. So when you take this derivative dA by ds, you can use this as a replacement for the 0 row and continue your analysis. If you see a 0 row, you can guarantee the system is unstable because it's either marginally unstable or fully unstable, which is in full respects of the scores unstable. Okay, that covers Routh-Hurwitz. If you can't be asked to do a to work on the closed loop transfer function, we can also work on the open loop transfer function. So we use something called the root locus. The root locus is the path taken by the roots of a transfer function upon varying a parameter, usually gain. So if I set the gain to 1, the roots are somewhere. If I increase the gain, what happens to the roots? It all relies on one idea, which is to say that if I have the axis, if I have the S-plane and I pick a random point on it like here, for this point to be a pole, it needs to fulfill two criterion, the magnitude criterion, which is that the k times the distance from zeros of g of s to s naught. So if I have 0 here, this distance and the distance from the poles, so this distance plus this distance must be equal to 1. If there's a pole here, then that's the distance, so on and so forth. The phase criterion is the sum of angles between zeros of g of s and sum of angles, and then the angle of k, gain can have an angle. This must fulfill the criterion 180 plus 360n. N is an integer. So if you get a number bigger than 360, you can just simply simplify it down to be modulo 360. So to sketch the root locus of a system, it builds upon these ideas. That means that you need to do a few things. First step is going to be to find P of s. P of s is basically you isolating the parameter you are changing from the given transfer function G of s. L of s, I guess. L of s is equal to GC of s, G of s. So again, I'm not taking the entire system, just the general smaller system. And what I want to do is isolate the parameter I want to change. Usually it's something like gain. So I'm going to take out the gain and I'm going to be left with P of s. The locus will always begin at the poles of P of s and end at the zeros of P of s. Again, we have a new characteristic equation and this is what we're going to be following. Based on the phase condition, there is another rule. The sections of the locus on the real axis must lie to the left of odd number of real zeros or poles. So if I have, let's say, a pole here, then over here there are 0. On this section, on the right of this there's nothing, so this won't be a valid area. On the right of this, in this section, on the right there's 1, so this is valid, this is not valid, this is valid, this is not valid. So the root locus is going to be here and here. The root locus will always go towards the zeros. So start at the poles, go towards the zeros. But the issue is we need to find the point at which it starts to move away from the real axis and the direction it moves towards. So the point at which it starts is called the centroid. This is basically the average of the this is the average of the poles that you have. Oh, sorry, I did not mean to do that. And the other thing is the angles that it will move towards. Usually just move straight up. So usually your usually your root locus looks something like it goes this way, reaches the centroid sigma, and it goes upwards and downwards. So the angle just becomes straight up. However, there may be different angles. The angle formula is given over here. It depends on the number of zeros and number of poles in P of s as usual. And you also have this very important n of zeros minus n of poles. This is used a lot. Number of zeros minus number of poles and zeros minus n poles used a lot. So remember, the first step is going to be to find P of s, write as zeros and poles. And you can also, so the first step is going to be drawing the real part of the root locus. So find the points at which it exists and just draw arrows pointing inwards towards the centroid. Put a dot on the centroid, have the graph move up from these points up to the centroid. So if this centroid isn't in the valid region, then it's going to basically shape itself to move around it. Remember, the root locus doesn't have to be gain. If you can rewrite the parameter you're adjusting as a factor of the characteristic equation and get P of s, anything goes. For more details, you can look at the lecture slides. Okay, so using root locus, we can do something called compensator design. This is used when you don't have a valid proportional controller that will do the job. So let's say you plot your root locus, your point doesn't fall on the root locus. Chat, are we cooked? No, not yet, you're fine. You can build a compensator. You can build a compensator which is of the form this is the general form of any compensator, lead or lag. If you have a compensator with z less than p, you get phase lead, and if you have z greater than p, phase lag. Why is this? Well, as I mentioned over here, the phase criterion, the angle g of s is given by this big brackets that I've expanded out. So similarly, the angle GC of S is angle Z minus angle P, and if Z is less than P, then when you draw it out on the points, so Z, P, if Z is less than P, then you know that the angle of this will always be greater than the angle of P. So if you have, like, let's say a pole over here, then yeah, that's what I mean. Moving on, if you have Z greater than P, you have phase lag. And if you don't know where to place Z, you just put it directly underneath the pole you're trying to reach. So if you're trying to achieve this pole, you can't achieve this pole with a proportional control, just put Z right under it so you get an angle of 90 degrees with it. And then this makes the calculation of angle P much easier. You can also derive the point at angle P much easier. A couple of things about adding a compensator. Usually you can approximate a compensator to do nothing to the system, but it does do something. It affects the other parameters, if only marginally. It degrades the steady state error, but it improves the transient performance if you have a lead compensator. So the lead compensator reshapes the locus itself, and it improves the transient performance at the cost of steady state error. The lag compensator can increase the value of the error constant, so improve the steady state error, but it will degrade the time it takes to reach that steady state. The thing is, we want the lag compensator to barely affect the root locus, so we do two very important things. We place Z and P very close to the origin, and we set Kc equal to K amp from the uncompensated design. So when you figure out that K failed, you calculated some K amp, the proportional controller gain K. You just set that as the gain for the lag compensator and set Z and P to very small values that still fulfill your lag compensating desire. Moving on, we now move into the frequency domain. And the frequency domain is pretty useful because, I mean, you guys have taken, if you've taken 3DY4, you know that we love frequencies. It's very fun. All hail filter. But more importantly, in real life, systems don't have polynomial inputs. Many times they do have sinusoidal inputs. They have frequencies of omega naught, and the output of a when you put a sinusoid into an LTI system, which is what we're always working with in this course, linear time invariant, the output will always be a sinusoid of the exact same frequency. However, the magnitude and phase may change. So the magnitude will change to a new value, and the phase may change to a new value. And the response is pretty simple. You don't actually have to do any fancy magic. All you need to do is figure out G of j omega naught. G of j omega naught is a complex value once you evaluate it, and the magnitude of the value will give you the ratio of the amplitudes, and the argument of the value will give you the phase change. A Bode plot, or a Bode plot, is essentially a way to visualize the entire frequency sweep. So if you put in every single value of omega from 0 to infinity, you're going to get the Bode plot. The magnitude is, this is how the magnitude looks, this is how the phase looks. There are two areas of a plot. This is the low frequency regime, and this is the high frequency regime. You won't have to draw a plot in the exam, but you will have to interpret many of them. So it's good to get familiar with them. I'll come back to low frequency and high frequency regimes later. Okay. Another thing we can also do is called the polar plot. Instead of plotting the entire response this way, we can always sweep omega and take RE and IM as a Cartesian plot. So for omega equals 0, we put a point. For omega equals 1, we put a point. 2, 3, 4, 5, 6, 7, 8, and then we just draw a shape. If you're struggling to if you've got a certain value at a point and you don't know how to split it, just simply rationalize the denominator. This is the fastest way to solve the question. This is the bonus tip. Another thing we do is what's called contour analysis of the frequency domain. A contour is a closed loop on a graph, but it has a direction. So if you remember, the root locus has arrows pointing to which direction it goes. Similarly, a contour has directions on which way it's going. So there's arrows pointing from the 0 point to the final point. The reason we use contours is because we don't even need the transfer function. If we have measurements such as the Bode plot, or if we have just the system itself and we can actually run some measurements on it by just plotting the frequency, we can easily get the entire contour ourselves. So no need for transfer functions. There's an important idea that's introduced, which is called contour mapping. So imagine a box in the S domain, in the S plane, which looks something like this, and the example given in the course is f is equal to 2s plus 1. So what you're going to do is you're going to take this box and scale it by 2, and you're going to shift it to the right by 1. So you're going to get this. So that is basically a mapping. So you are mapping S-plane to f of S-plane. A mapping is the action of taking every single point on a contour in one plane, putting it through a function, and putting it on the other plane. There's also the idea of encirclements. If a contour goes around a point in the clockwise direction, it's considered an encirclement. And one important thing we do is attributed to a guy called Nyquist. He figured out that using this characteristic equation, 1 plus ls equal to 0, where ls is the open loop transfer function, we can do a lot of stability analysis. So what is Nyquist contour? A Nyquist contour is basically a semicircle in the S-plane. It's just this. That's it. It's just that. But if you have poles or zeros of your function on the j omega axis, it will avoid them. So if you have a 0 here, it's going to bend around it. So you're going to get something like this. If you have a pole, similar thing. Then Nyquist came up with probably his most important theorem outside of his sampling frequency thing. The number of closed loop poles in the right half plane is always equal to NL plus PL. And the stability of a system, remember, is determined by the number of closed loop poles in the right half plane. So if this number is 0, then you're goated, like it's pretty easy. So what is PL? PL is the number of L of S open loop poles in RHP. This does not include marginally stable poles. This is very important. In every other stability criterion we said marginally stable is unstable. For the case of Nyquist criterion, it doesn't include those. So any open loop poles in the RHP are counted as PL. LFS is the one that I've shown here. And NL is the number of clockwise encirclements of the point 1, 0. Encirclements are made by the Nyquist contour image under LFS. Yapping. Sorry. Take the Nyquist contour, put every single point of it into LFS, get a new contour, I'll show that on the next slide, and check how many times that new contour circles the point -1, 0. That is NL. A couple of things you can realize by this. First off, you can't use a Nyquist contour as is. This is an example of the Nyquist contour, and what we're doing here is we're throwing it into a, this is the Nyquist contour in S-plane, and this is the Nyquist contour in LFS plane. So you can see that someone's taken every point, put it in an LFS function, and got you this plot. In this question, you can see there is no encirclements at this point, so you're good. There's no N of L. So the number of encirclements of the RHP is just P of L. Importantly, if there are no encirclements, any system that is stable in the open loop will remain stable in the closed loop. If you are ever struggling with these frequency domain questions, feel free to check your answers with root locus in the RH table. In fact, there is a question in the exam which asks you to find a K1 or K2. Just use the RH in that case, since the Nyquist can't be precise enough to do it. So that's what they expect you to do, actually. Another thing is that the Nyquist criterion, and by its extension the Bode plots, give you a cool little ability. They tell you how close a system is to being unstable. We call these terms gain and phase margin. The gain margin is, well, let's assume the system has a unity gain. How much can I push the gain before it becomes unstable? There are two ways to find the gain margin of a system. The first is the distance from the origin to the real intersection. So imagine if this this is not a very good example. I'll draw out another one here. Imagine a system that has a response that looks like this, and this is -1. There's no encirclements yet, so we can say that this still has a gain margin. We know that when this encircles -1, the gain margin goes away. So the distance from the origin to this point is used in this denominator to get the gain margin. If you have the Bode plot, you can overlay the Bode plots on top of each other and find the omega at which the phase value is -180. Then you look at the magnitude value at that point and find the magnitude values, absolute value essentially, so the distance from 0. And that becomes the gain margin as well. Similarly, the phase margin can be found from the Bode plot using the where you overlay both the plots, find the point where the magnitude value becomes 1, or in the case of the decibel plot, it's 0 dB. In this case, the phase delta from 0 is the phase margin, the change in phase. This point is very important. It is known as omega C, the open loop crossover frequency. You'll be asked this in many questions. You can also find it using the diagram. The diagram over here, I have just put a picture. I didn't really have space in the slide, and yeah, I was trying to lay out the slide to be like compact, and I just put it in the corner. But basically, this angle L of j omega C is what I'm referring to here, the angle between the positive real and the intersection of -1 magnitude. So this angle is equal to the phase margin. This angle is 180, so this delta PM is equal to 180 plus angle L j omega C. So quick formula for you guys. And this is the angle L j omega C. I couldn't figure out how to explain it in words, so that's why I have this picture over here. Moving on. Oh, sorry, I forgot to mention, distance from origin to real intersection. The real intersection is the point at which this curve finally goes back into the real line. That's what I mean by real intersection. Okay, let's go to designing in frequency domain. As I've mentioned, we can do design in the Laplace domain. Let's see if we can do design in the frequency domain. We want to figure out ways to relate the quantities that we know in the frequency domain to performance parameters. So here's a quick relation. Phase margin, put this in your formula sheet. This is a phase margin equation. It puts phase margin in terms of zeta. Zeta is a function of PO, so we can say phase margin is a function of PO, and if you're given a percentage overshoot, you can design a phase margin for it. Or if you're given a percentage overshoot, you can check the phase margin and be like, oh, this doesn't have enough phase margin, it's not going to work. There's an approximation you can use. If you have a zeta less than 0.7, the phase margin is approx 100 zeta. Then there's the term bandwidth. The bandwidth is the distance between the well, you know what the bandwidth is. If you have a curve that looks something like this. This is the peak, and you want to find the points. This is peak. You want to find the points as peak minus 3 dB, and this is one point. This is the other point. The distance between these 2 points is omega bandwidth. So the omega bandwidth actually finds a relation between omega n and zeta squared. So you can find the phase margin, you can find the bandwidth, and you can then find the bandwidth. But more importantly, we also know that omega n can give you TSS, so that's another parameter solved. But what if you don't want to do all of this for the closed loop? You just want to work on the open loop. No problem. You just have to find the open loop crossover frequency. As I said, it'll come back. Omega C is equal to omega n and this formula. So if you're given a phase margin, you can relate the settling time to the open loop crossover frequency. If you're not given a phase margin, you can find one using the required percentage overshoot. And this enables us to design any controller we want using Bode and Nyquist criterion, because once we have this, we can start designing stuff similar to how we do with root locus or with Routh Hurwitz. So some things that we usually look at. If a loop must be stable, well, we can use the Nyquist criterion, the Nyquist stability criterion. If we need to find a max overshoot, a max percentage overshoot, phase margins given. If we need a settling time, we have the open loop crossover frequency. If we need the steady state error, well, the type number depends on the slope of the Bode plot per 20 dB decade. So if you have a Bode plot with a slope of, let's say, 40, then you know that its type is 40 by 20 or it's a type 2. And you know the type system that was in the slide that I mentioned earlier. So what do you do with all of this? Well, you want to try and shape the loop using a lead compensator. What is loop shaping? It's basically trying to mold the loop to whatever you want it to be. And let's talk about how you want to do that. First off, you want a controller with a magnitude plot that's an LPF, like I've shown over here, low pass filter. Its transition should be around omega C, the open loop crossover frequency. That is also, if you remember, the point that we refer to for measuring the phase margin that I showed in the previous slide. And for a good phase margin, the magnitude plot should have a slope around minus 20 dB per decade at the point that we measure the phase margin. Okay, so far so good. So moving on, we can figure out how do we design a lead compensator. This is a quick lead compensator. I instead of rewriting this in terms of P and Z, I just put it in terms of alpha and tau. I'll explain why in a second. So first off, we set the phase margin that we need and omega c based on the criterion that we have over here. Then we have to find a gain where kg of j omega c is equal to 1. This is important. We need to basically find a point where once we plug in the open loop crossover frequency we found, we need to find a k which makes this go to 1. Once we find a k, we need to find a we need to find, using what we already have, we can find the phase margin using the angle of, we can use the angle criterion to find the phase margin. This is using the proportional control alone. However, if this k just doesn't work out, there's no valid k for what we actually need. Like we need a phase margin that's much larger. No problem, we can use a compensator to add phase margin to the system. So we first find alpha as 1 plus sine delta phi. Delta phi is the phase that we need to add on. So the current phase must be something, the phase margin needed is something else, we need to add on some phase, so we use this formula. We also write a relation P is equal to alpha z and omega c is equal to square root zp. These two combined is, you have two equations, two unknowns z and p, solve for z and p, and you'll find your controller's pole and 0. The last part left is to find kc of your controller. To find kc of your controller, simply plug in the z and p you found, plug in the omega open loop crossover frequency, and then you're going to solve this, get kc from this equation over here. Okay, let's talk about lag compensation. Lag compensation has a benefit of being able to improve the steady state error as mentioned, and it can increase the low frequency gain, but it reduces the phase margin. I'll get to that in a second. So the main thing we usually use this for is to increase the low frequency gain or to attenuate. I also want to mention here reduce LF disturbance. So if there's a low frequency disturbance, something like wind or something like that in a system, it's a very low frequency. Having a lag compensator helps reduce that. So how do we do this? It's pretty simple. We first find the alpha that we need to increase the low frequency gain or reduce the low frequency disturbance. And we put the lag 0 much less than omega c, usually omega c by 30. This is to prevent the impact of the phase margin. If you don't do this, the phase margin will crash, because remember, a lag compensator lags the system and reduces the angle. Then we can do a similar relation. We can find pole and zeta, so we know where the 0 is. We can find the pole very easily, and kc is equal to k amp, similar to how we do for the lag controller in the root locus world. K amp is found by using omega c in the magnitude criterion. So I'm going to use the magnitude criterion K amp gc of j of this guy over here. I'm going to plug that in. Okay, so far so good. If you have a question that asks you to hit a phase margin, a crossover frequency, and a steady state error or a low frequency disturbance filter, you will need to use a lead lag controller. So again, this philosophy of designing a lead lag controller carries over from root locus. Design the lead controller first, check its performance, and then see if you need to add a lag controller onto it. As a quick aside, there was a question I saw which is about low frequency disturbance attenuation. This might sound confusing. Basically what it's saying is there's a TD of S at a very low frequency and we need to attenuate it. Remember that if TD of S is low frequency, we can just take this guy, H of S is equal to 1 here. So that's what they have over here. I'm taking the limit as S goes to 0 because it's a low frequency term. So again, S here being the value is going to go very close to 0, low frequency. And this is always less than minus 10 to the power minus attenuation required over 20. So if let's say they ask for 40 dB of attenuation, then this is going to be minus 1 over, not minus 1 over 100, just 1 over 100. So you can say that for 40 dB of attenuation, we need the signal to be 1/100th of its actual value. So the limit, so this response must be 1/100 of the TD of S. Assuming that TD of S is 1, this needs to be 1 over 100. That concludes it. That was a pretty short and sweet one. I will try and upload the answers as soon as I can. I hope you guys enjoyed this. I welcome questions anytime you like, and I would appreciate if you guys could, if you enjoyed this, you guys could donate a couple of dollars to my Ko-fi. I'm trying to pay for my cat's surgery right now, and any little dollar is appreciated. Have a wonderful day. Good luck. I'll see you all on the other side.